Hey guys, back with another video. In this one we have this really interesting integral. We have an integral that has all of the integers from 0 to 10. It has, and I've underlined them, it also has the bounds of infinity, it has the square root of 2, the square root of 3, it has the lucky number 21, it's got the natural number e, the imaginary number I, the trig functions of cosine and of sine. It's got the choose function, it's got the floor function, it has a big square root, a double integral, it's got x and y. The only thing that it is missing is pi. So let's evaluate this integral, and we know that this integral is going to be equal to some value I because it is a definite integral. So we can square both sides and then it'll be equal to I squared. So we have 0 to infinity, and let's pull the negative out of here. So we'll flip that around, which means we can flip our bounds around. And we also see this 7 choose 5, and this is equal to 7 factorial over 7 minus 5 factorial, which is 2 factorial times 5 factorial. So this is 4 over 21, and then times, well, 7 factorial over 5 factorial is just 7 times 6, so over 2 factorial. 21 is 7 times 3, so 7 times 3, the 7's cancel out, the 6 cancels out with 3 and 2, and we're left with a 4. So we get 4 right there. We can combine this e with that function of e, so we get, that'll be e to the minus x squared minus y squared, and then plus 18. And then, okay, well, this will be 2 cosine squared, and root 9 is equal to plus or minus 3, but cosine is even, so it really doesn't matter if it's plus or minus, so that'll be 3x. And then I to the 6 is equal to I squared, which is negative 1, so minus 1. And then, well, root 2 plus root 3 is approximately equal to 3.14, which is slightly greater than 3, so the floor function of both of those will equal 3. So that'll be, well, we have to flip them around because we took the negative out, so it'll be cosine of 3y, and then minus sine, and then sine squared. It was cosine squared, yeah, and then sine squared of 3y. dx dy, and this is equal to I squared, and we're solving for I. Well, now let's use some of our trig identities. This is the same, e minus x squared minus y squared, then plus 18. Well, this is equal to, well, it'll be equal to cosine of 2 times whatever's in there, so that'll be cosine of 6x. And then here, I recognize this identity. This will be equal to cosine of whatever's in here, and then times 2, so that'll be cosine of 6y, and then dx dy is equal to I squared. Well, this looks very symmetric, so let's separate the x's and y's. This is 2, and then e to the minus x squared plus 9 cosine of 6x, and then that is times 2e to the minus y squared plus 9 cosine of 6y. And whenever you have an integral, a double integral with the same bounds, and you have the same integrand being multiplied by itself twice, well, then you can actually just write it like this. So this is 2e to the minus x squared plus 9, and we'll choose 9 because it's more conventional, so of 6x. Well, this is equal to this squared, or dx squared. This is equal to I squared. And now if we take the square root of both sides, so it's interesting, we squared it, and then now we're taking the square root. So this is 0 to infinity, and then 2e minus x squared plus 9 cosine of 6x dx is equal to I. So really, if we just pause for a moment, this integral is actually just equal to that, and that's pretty fascinating how it simplifies all the way down. So let's take out some constants. We get e to the 9th, we can take that out, and integral 0 infinity e to the minus x squared, and then cosine. And let's take this 6 out and put a t, and we will apply the Feynman technique. So we'll define another function f of t where I is equal to f of 6. If we differentiate with respect to t, we get f prime of t is equal to minus 2e to the 9th t integral 0 infinity e to the minus x squared sine of tx dx. And now, this is not a t, but rather an x. We took the derivative with respect to t, so we need to bring the x out. Well, now we can apply integration by parts. So we have integral u dv is equal to uv minus the integral v du. So our u is equal to sine of tx, and our du is equal to t cosine of tx. Now we're taking the derivative with respect to x. So our v, x e to the minus x squared, and then our dv is equal to, well, that'll be minus 1/2 e to the minus x squared, because if we take the derivative, so if we take the derivative of this, then that would be, or rather this is dv, and this is dx. We can get rid of the dx right there. If we take the derivative, then we'll multiply by a negative 2x. The negative 2 will cancel with the 1/2, and then we will have our original function. So f prime of t is equal to minus 2e to the 9th. This is times uv. So our uv is minus 1/2 e to the minus x squared sine of tx. And we're evaluating from 0 to infinity. And then minus the integral v du. So that'll be a negative 1/2, and we'll have to cancel out this 1/2. So that'll be plus 1/2 e to the minus x squared, and then our du. So we'll have a t cosine of tx dx. And this is 0 to infinity. Well, now if we evaluate this as x approaches infinity, it'll equal 0, because it'll be, sine will oscillate forever, and that will be over an infinitely large number. And then if we evaluate it at 0, well, sine of 0 is 0, so that'll be 0 minus 0, and that cancels out. Now we get f prime of t is equal to, well, our 2 will cancel out with our 1/2, and we'll get a minus t e to the 9th times the integral of 0 to infinity of e to the minus x squared cosine of tx dx. Well, if we notice from up here when we defined our f of t that this was equal to f of t, and it looks a lot like this. The only difference is we have these constants out front. So what we can do is we can multiply both sides by 2, and we can divide by this negative t. So we get 2 over, and then negative t, f prime of t, now we multiply by 2 on this side, is equal to 2e to the 9th times the integral of 0 to infinity e to the minus x squared cosine of tx dx. And what this is equal to is and I'll change colors so it'll be easier. What this is equal to is this, except we'll actually bring our negative back over. I'm not sure why I put it on the left-hand side. So now we know that 2 over t f prime of t is equal to f of t. Well, that's pretty remarkable. We now have a first order separable linear or differential equation. So we have 2 over t, and then our f prime of t is equal to f of t. And let's just make sure we got those negatives right before we move on. So we had brought out this t right here, and we had brought that out from this integral, and I'm not really sure why we had brought that out as a negative. I'm pretty sure that was supposed to be a positive. So that's a t, and which means that we shouldn't have gotten a negative on only one side. We should have a negative on both sides. So this is actually negative 2t and a negative right here. So now we can evaluate this, and let's get all of the other terms on the right hand side. So df dt is equal to minus t over 2 times f, which means that, well, we can solve this differential equation. 1 over f df is equal to minus t over 2 dt. If we take the integral of both sides, then the natural logarithm of f is equal to minus t squared over 4 plus c, which means that f is equal to c e to the minus t squared over 4. Well, we need to solve for our initial condition c, or for our constant c. So using an initial condition, if we look at our f of t when we defined it earlier, note that for t, and we're using this function right here, for t equals 0, then we will get, well, f of 0 is equal to 2e to the 9th times the integral 0 to infinity. Cosine of 0 is 1, so this will be e to the minus x squared dx. And this integral is exactly equal to half of the Gaussian integral. Remember that e to the minus x squared is even, so if you split the bound in half, then you'll get half the value. The Gaussian integral is equal to the square root of pi, so this will be equal to the square root of pi over 2. So f of 0 is equal to 2e to the 9th times root pi over 2. The 2's cancel out, and it's equal to e to the 9th root pi. So we know that we have e to the 9 root pi, and this is equal to c e to the 0, which is just 1. So our c is equal to e to the 9 root pi. So f of t, our function, is equal to e to the 9 root pi e to the minus t squared over 4, which is equal to root pi e to the minus t squared over 4 plus 9. And we needed to evaluate this at 6, so f of 6 is equal to root pi. If we plug in 6, that'll be negative 36 over 4 is equal to negative 9. If we add 9, that equals 0. E to the 0 is 1. So f of 6 is equal to root pi. If you recall from earlier, if we can find it, our f of 6 is equal to I. So that means that our I is equal to the square root of pi. And our I is equal to our integral. And the reason that we did not have pi in our integral is because it was actually equal to pi, or rather the square root of pi. If we get rid of the square root on both sides, then this is just equal to pi. Well, I hope you found that video helpful, or at least you enjoyed it. It was really fun to make. It took me a while to come up with this integral and to get all those values in there, but it was super fun. I hope you enjoyed. Please leave a comment below if you had any questions. Please subscribe to help the channel, and I will see you in the next video.